The planet Mars was born about 4.6 billion years ago in the early solar system. Its formation began in the protoplanetary disk, a cloud of gas and dust orbiting the newborn sun. In this disk, tiny particles collided and stuck together, forming increasingly larger bodies, planetesimals. Gradually, they gave rise to the embryo of Mars, a protoplanet. Mars formed relatively quickly, in just 4 million years. It became the fourth planet from the Sun and acquired a solid surface. Inside the planet, there was an active core that generated a magnetic field. Around 4 billion years ago, during the so-called late heavy bombardment, the surface of Mars was struck by powerful meteorite and asteroid impacts. The entire inner solar system, including Earth and the Moon, underwent intense cosmic bombardment. These collisions triggered volcanic eruptions, altered the climate, and vaporized surface water. Some meteorites delivered organic molecules, the building blocks of life. The heat from impacts created subsurface zones with liquid water, where temporary but habitable conditions may have formed. After the bombardment ended, a period of active volcanism began. Magma from Mars's interior rose to the surface, forming vast lava plateaus. The most impressive result was Olympus Mons, the largest volcano in the solar system. It reaches a height of 25 kilometers, and its base spans more than 600 kilometers. Constant eruptions lasted for millions of years, and the heat from magma created local conditions suitable for liquid water and possibly life. The water era on Mars lasted from about 4.1 to 3.5 billion years ago, during the Noachian period. During this time, the climate was warmer and wetter than today. Rivers, lakes, and possibly even oceans existed on the surface. This is evidenced by dried riverbeds, deltas, shorelines, and mineral deposits formed in the presence of water. Gradually, Mars began to lose its atmosphere. After its magnetic field weakened, the solar wind, a stream of charged particles from the sun, began stripping the planet's atmosphere into space. This process continued for millions of years, resulting in a significant drop in surface pressure. Liquid water disappeared, and conditions became cold and dry. The remaining atmosphere became too thin to retain heat, moisture, or support active geological and climate processes. This process drastically changed the face of the planet. Beneath the surface of Mars, there are vast deposits of water ice, especially in polar and temperate regions. In some places, layered ice sheets and salty underground lakes remain hidden below the surface, capable of staying liquid even at low temperatures. These aquifers are well insulated from external conditions and protected from radiation and temperature fluctuations. They still exist today, representing an important part of Martian geology and a potential habitat for life. The Martian crust consists mainly of basaltic rocks rich in iron and magnesium. Iron oxides present on the surface give the planet its characteristic red color. Silicates, especially olivine and pyroxene, are widespread. In various regions, clay minerals, carbonates, and sulfates are found, formed by interactions between rocks and liquid water. Underground, there are deposits of salts, including perchlorates. The chemical composition indicates processes such as weathering, hydrothermal activity, and chemical evolution involving water in the past. The soil contains silicon, aluminum, sodium, potassium, calcium, and traces of sulfur and chlorine. Mars's mineral composition reveals a diverse geological history and supports the hypothesis of its active geochemical past. Mars has two small moons, Phobos and Deimos. They are dark, heavily cratered, irregularly shaped bodies. Phobos is the larger and closer of the two, orbiting very near Mars's surface and gradually moving inward. Deimos is slightly farther away and moves more slowly. Both moons are cratered and dusty, lacking atmospheres, and resemble asteroids in composition and appearance. Their origin is linked either to the capture of ancient asteroids or to debris from a collision between Mars and a large body. Despite their small sizes, Phobos and Deimos play an important role in studying Mars's gravitational and dynamic history. Mars once had conditions suitable for life. During the water era, rivers, lakes, and a humid atmosphere existed. In such environments, simple microscopic organisms could have formed. Even after atmospheric loss and climate cooling, stable underground aquifers remain, shielded from radiation and temperature extremes. In these enclosed ecosystems, rich in salts and minerals, biological activity could have persisted for billions of years. Modern data show the presence of methane in the Martian atmosphere, which may be related to subsurface microbial life. Subsurface zones remain key areas where life might not only have emerged, but may still exist. The Martian surface still holds the traces of that era: craters, water deposits, and remnants of channels. They have been preserved due to the thin atmosphere and low geological activity. These scars allow scientists to study the processes that took place in the early history of the solar system. Thus, the era of meteorite impacts not only reshaped Mars's landscape, but also played a crucial role in its climatic and possibly biological history.
This is where this amazing story ends. Like and subscribe to the channel, and also write comments. I will be very interested to read. See you soon.